my first time here. It's very well known that if you have a liquid and you cool it down, they can survive in a supercooled metastable regime, right? No, okay. It's here. If you continue to cool down the system, this supercooled liquid has only two ways, ultimate fate, or crystallize or become amorphous phase. This kinetic of crystallization mechanism, it's very, very important in several areas, in snow precipitation, crystallization, and also in industry. You can see the importance of this mechanism to create a single crystal, metal casting, drug design, and production of glass ceramic material. To properly understand this atomic dynamics of supercooled liquid, we have to have information about two characteristic time. One is the relaxation time, which is the intrinsic atomic diffusivity to leads to a structural rearrangement of the supercooled liquid. And the other one is nucleation time, which is the time necessary to form the first nuclei, which can grow as a whole. The race of these two relaxation time will decide that who happens first. If the nucleation time is smaller than relaxation time, you will have a crystallization of your material. In the other side, you have a glass or amorphous material, right? The people used to call the temperature in which nucleation and relaxation time equal are the kinetic spinoidal. It's not the classical thermodynamic spinoidal temperature. It's just a name where they come together. Okay. This kind of analysis has been very few reported in the literature. Experimentally, I know only these two systems who they can measure this characteristic time. And theoretically, using simulation, pressurized silica, supercooled metal, binary Lennard-Jones, and one semiconductor barium sulfide. These are the systems I could find in the literature describing this kind of system. We decided to study zinc selenide. They have several very interesting properties. It's a semiconductor, direct wide band gap, low absorptivity. It's using lens, windows, laser diodes, and it can crystallize in two phases, zinc blende and wurtzite under ambient conduction. Zinc blende is stable, more stable than wurtzite. Our approach was molecular dynamic simulation. To do that, we need one interatomic potential for the system, and this interatomic potential must show that this system can show spontaneous crystallization. Otherwise, you cannot compute nucleation time, for instance, right? I use this Wachista-Raman potential, which includes two-body interaction and three-body interaction. The two bodies, very simple, is one steric repulsion, screening Coulomb, charge dipole, and dipole-dipole interaction. And three-body takes into account the bond bending and bond stretching interaction. That's it. We have some parameters we have to find out. The parameter, I use these quantities to find out the parameters of my potential. cohesive energy, elastic constant, bulk modulus, and elastic constant. And these are the results reproduced using this value as a guide. Extra parameters, which was not used in the simulation, the parameterization, is shown here. C12, 44, and melting temperature of the system. The energetic of the system shows that the zinc blende structure is more stable than wurtzite by some millielectron volt, and under pressure we can show that the system has a structural phase transformation induced by pressure. Right? To be confident about this potential, we compute extra quantities. For instance, dispersion relation, vibrational density of states, specific heat, and the compressibility of the material, and compare with several experimental results we found in the literature for this material. The by temperature is also in very good agreement. So, we have a very good potential, describes several properties of the material. The system also shows spontaneous crystallization. So we are ready to compute the characteristic time we are talking about, nucleation time and relaxation time. Two system size was simulated, 17,000 and 33,000 particles. And the first one was melting. Start from zinc blend, the system show a mechanical melting here, and when you cool it down, you will have this figure. In the crossing of these two lines is defined the glass temperature, the TG. So we have two regions. One is very deep supercooled liquid, and the other one is very solid supercooled liquid. Here, we can compute nucleation time, and here we can compute the relaxation time. Why? Because the temperature is too high. We are not able in computer, in the simulation time, observe the birth of the first nuclei. So below 1000 K, we can compute the birth time. We compute for the street temperature for these two systems. We characterize the solid-like particle using this bond order parameter given by this expression. This is harmonic, spherical harmonic. And computing that, we can compute, and this is just one snapshot of the system for the three temperature as a function of time. And you see that for small temperature, you can see when crystal starts to born here, and it starts to increase, and you have a full crystallization of the system. Increasing the temperature, you have to wait longer to see the first nuclei, and increasing again much longer. So depending on the temperature, you must wait much more time than the low temperature, much more difficult to crystallize. And these are the results, right? We compute for these two systems I have studied, the nucleation time in picosecond for 1,000, 950, and 900. Recall that the steady-state nucleation rate is given by that, and I know the size of the system. I can compute the steady-state nucleation rate. For this temperature, you see it's almost the same, almost the same, almost the same. This is a typical characteristic of the system at that temperature. So I can try to have some hint. What will be the time necessary to observe the first crystal for a system very large? For instance, one system with a 1 micron cube in size. And you see that the size is very, very long, right? 10 to minus 4, 10 to minus 5 picosecond, we can have that. In the other side, above, very shallow supercooled liquid, the time necessary to observe the nucleation rate will be impossible. So we use, to compute the structural relaxation time, in this interval, we compute the intermediate scattering function given by this expression. And the long time, the long tail for this f of q is given by the Kowalski-Williams-Watt law, which is a standard exponential function, right? This plateau we have here is just because when you the particle starts to create a cage, and the one particle becomes locked in this cage until it can escape and go to other part. So fitting for each temperature, this Kowalski-Williams-Watt expression, we can compute the tau alpha and beta, right? And these are the results for tau alpha as a function of temperature and decrease, and beta goes to 1 when the temperature goes in the liquid phase. At the liquid phase, the relaxation is completely exponential, right? Taking the tau alpha as the average for these two species, zinc and selenium, and the same for beta, and using this expression given by these people here to relate, to make the relation between the relaxation time and tau alpha, we can have extra information with the MD, with the diffusion. It's very easy for molecular dynamics to compute the mean square displacement, and you have the diffusion as a function of inverse temperature. The Arrhenius law break down around this temperature here, and using the green Kubo relation, I can compute the viscosity, and viscosity have this behavior. There are several theories trying to describe how the viscosity change with temperature. Some of them are the Avramov, Miev, I forgot the name of the guy. And I forgot the name of the other guy. So, very deep supercooling, I can compute that. In shallow supercooling, I can compute tau r. So idea how to compare these two systems. How can I extrapolate these two characteristic time to other temperature where I don't have information directly from molecular dynamics? For tau n, we use the classical nucleation theory. You say that the classical nucleation theory can describe very deep supercooling regime. And for relaxation time, you use one expression called Miega, which is the name for the three persons who propose the dependence of the viscosity as a function of temperature. Mauro, Yu, Ellison, Gupta, Allen, Miega, which given by this expression here. So in tau n, we say the steady state crystallization is given by that. It is this expression in classical nucleation theory is given by this expression, so I can fit A and B with my results, and tau r, I can use the expression from Miega using the viscosity. Doing that, I have this here. This is the characteristic time. This is our nucleation time, and the dashed lines are the fitting, and this is the time computed from viscosity, and this is the Miega fitting, and this is the same result when you suppose one very large system with 1 micron cube in size. Several experimentalists use the expression of Max relation, relating this relaxation time coming from viscosity, and G is the shear modulus at infinite velocity. The first result is that the Maxwell relation is always underestimate the time of relaxation. Above 1100 K, we can see that the relaxation time is always smaller than tau n, nucleation time. But for a large system, the nucleation time is always smaller. The critical cooling rate required to avoid the nucleation is defined by this expression by Ullmann and Nong, publishing in Journal Non-Crystalline Solids in '72. So using our system size, we can compute the critical cooling rate to be this 5 and 18. We are using 1. So in our simulation, spontaneous nucleations are always present in the system, right? In conclusion, we could compute both nucleation time and relaxation time. We show that the relaxation time using Maxwell relation gives order of magnitude smaller than the correct one. This result is confirmed by some experimental results we can observe. For shallow supercooling, the system always relaxes before nucleation. For TKS larger than glass temperature, the system crystallizes before becoming a glass. And TG refers to a residual supercooling liquid which already contains several crystalline nuclei formed during the cooling path, because we are using one cooling rate which always will show some crystalline material. This work was done in collaboration with Professor Edgar Zanotto, which is the head of the CERTEV in São Carlos, with Leila Separdar, which is a FAPESP fellow, and she comes from Iran and is doing a PhD with us. That's it. Thank you.
So thank you for the talk. Are there any questions?
I have a more technical question. So when you observe the nucleation in your simulations, do you need to start from a small cluster, or does it spontaneously form?
Spontaneously. That's because the potential is good. I'm sorry to say that. If you take, for instance, another kind of potential to describe materials, you never see the spontaneous crystallization, right? That's a quality of the potential you have to put.
I have a question. Is it possible in these materials, in these regimes, to define some kind of spinoidal?
The thermodynamic spinoidal?
Well, in the sense, at least effective.
Yes, I believe so. Yeah.
When you cross.
This crossing of these two times, you call the kinetic spinoidal temperature, is not the thermodynamic spinoidal. No. They're different. It's just the name, the temperature where the two characteristic times crosses. That's it.
Okay. More questions? Well, if not, let's thank again the speaker. Also for the timing.